So usually we talk about our parents in terms of people. I'll talk about them about where they come from as well. So my mom, does anyone recognize the bottom photo? Yeah, all right. So my mom is from Guatemala, and she actually left Guatemala when she was 15. She was escaping an arranged marriage. She had a grandparent that's sort of forged her parents' signature to come to the U.S. To go to school, where eventually she met my father in Boston. I won't ask about that city, and that's where my family's background comes from. I grew up. They made the interesting decision to move to Bakersfield from Boston. And does anyone? I know we already heard about Bakersfield, so I'm really impressed that we've heard about Bakersfield a couple times during this conference. But it is a challenging place to grow up as a Latino student that likes school. And then I always thought it was a tough place to live, but my parents were always like, hey, no, this is like a great place to raise a family. And I was like, really? And then finally, there was vindication. It's a 20-year study, and it was ranked number one. And that said, like, Fresno's way up there too, guys. So, that was what I felt when we were growing up there. And, it was really about the opportunity for the communities that live there. It is among the worst environmental disasters a place to live right now. It still is. It's only an hour and 45 minutes north when there's no traffic from here. It also has some of the worst violence, worse segregation, worse economic opportunities, and really that's how you get to the number one spot as you round all those things up. And it was particularly focused on being a child in Bakersfield. And so, I think what we've heard is a lot of people have come from very different backgrounds to get here today. And I don't think I particularly had as challenging time as many students in this room, but I think it's worth acknowledging that, and this is going to be a theme you're going to hear a lot, math and in data science is a very human endeavor. We've heard maybe, my favorite quote so far, among many quotes, was the comment around the topologist is like, and this is Richard, right, who said, what if no one read your papers? Would you be okay with the math? And the first gut reaction was like, yeah, no problem. And then it took a day and they're like, no, I would stop doing it, right? So I do think that there's the journeys also that we've heard have been very nonlinear and scattered, and I've had a very similar experience. I thought I was going to be a filmmaker when I was in high school, and I got in a lot of trouble. I blame that on Bakersfield as a kid, but I was also a kid that maybe was in the principal's office quite a bit. But I had somehow gotten my way accepted to the University of Pennsylvania. I didn't really want to go, but my parents were like, are you crazy? You should go. And I went, and I hated it. I had a roommate, just careful, right, this is being recorded, from Wharton. And if you know anything about Wharton, our former president also went to Wharton. And it was a really unfriendly place, and I thought I was going to do physics since I wasn't going to be able to do film there. And I walked up to the calculus professor, I think his name was Professor Denogi at the time, and it was a room of 350 people, and I was like, oh, why did I come here? I had a full ride to UCLA and Berkeley, and he was like, I don't know, you should go back, the weather's better. And so I dropped out of UPenn, so thinking about failures and things that didn't work, I just didn't think I was gonna make it there, and so I didn't like it, and so I put in some transfer papers. I applied to a bunch of schools in California again, and my one advisor in UPenn was like, look, I went to Caltech. It's a great school. Don't apply there for undergrad. It's a horrible place to be an undergrad. God, I'm really getting a little candid here on camera. But he's like, have you ever heard of this school called Harvey Mudd? You should go there. The things you don't like about your experience at UPenn, it'll be different there. And in the meantime, I came back to Bakersfield, and I walked into the math department at Cal State Bakersfield, and I had some shared advisors now with people in the room here. So Bakersfield's gonna rise a little in terms of math department. And I asked, can I take a class? Can I TA? Could I get a job? And they were like, do you know it was Kamel Haddad, if you know Professor Kamel Haddad. He said, do you by chance know maple? Does anyone know maple in the room anymore? Oh, thank God. Okay, so it was like 1998, and like they had just adopted maple, except no one in the department knew any maple. But they were told it's time to start using maple. And I said I had just taken a maple math class, and they're like, great. You could TA the maple section in calculus as long as you enroll in a class. I enrolled in ODEs there. I loved it. And when we talk about encouragement and nudges, you know, when I was done with that course and I was done TAing, Kamel's like, look, I know you're leaving. You're going to go to Harvey Mudd. First off, switch from physics to math. Second, you should really apply to this RU called CMU. And I really am hesitant to ask, does anyone remember or heard of CMU? Yes, my people, I know. So I see some. So that to me is like kind of the story of this community, is that there was people trying really hard to bring people into this field, and CMU happened to be an RU that was in the University of Puerto Rico, and it lasted just 3 years by two amazing people, Herbert Medina and Yves Rubio, and that was when I really fell in love with mathematics research, and I knew I wanted to be an academic from there. I went to Mudd, it was great, so that's CMU down there. It's hard to see, but it's actually centered on Puerto Rico. Had great mentors there, but it was really a place that you can really have your imposter syndrome take off. Harvey Mudd is a place that is extremely competitive. I didn't quite realize the place I was getting into, but I also was okay with that, and that, you know, I could adapt to thriving in a place where people were working really hard. And I found mentors that worked, and I think I've heard a lot from people today about finding those mentors to get you through difficult places. Mudd is a difficult place. By the time you leave it, you don't want to go back for a while, and well, it might be better now, but back then it was a place like that. But then, you know, I asked a bunch of mentors what I should do next. You should go get a PhD. I went to Boston University. I was following a girlfriend, now wife there. And so it was a great department to do complex dynamics, which is what I thought I was going to do. I was actually an algebraist. We're going to get to that today as an undergrad. And then I was doing complex dynamics. I was a nice graduate student. I was told, what should I do? And we heard the advice today, write papers. You have research capability, write papers. And so I went to graduate school, and while I was a graduate student there, I wrote 14 papers, all, you know, published in A-level journals, because I was following the advice of people. It says write papers, but I moved around a lot in that time, and we'll get to that. I changed fields, I switched advisors twice. We could talk about what that means, all good. But in the middle of all this, I was doing a lot of research in a community that was not a lot like my CMU community or the community I grew up in, Bakersfield. And so, does anyone know what AMC is? Oh, that one hurts. Okay, so AMC, it was an REU by Stephen Workus and Erica Camacho. All right, okay, I got a couple. So I had this siren call to think about, again, how can I work with my community while still balancing the needs of becoming a research mathematician. And I found some mentoring as a graduate student at Summer RU. I know some people are doing that right now in Prime, which is exciting. I say thumbs up to that. And again, I was able to contribute back to that community, learn how to mentor students. It was an extraordinary experience, and again, great faculty mentorship that I got there. When I finished at Boston University, my advisor said, I think you should get a postdoc. I said, yeah, sounds like that's what I'm going to do. And he's like, I think you should go either to Warwick or Princeton's IMA, Institute for Advanced, there you go, thank you. And I said, great, but I wanted to go back to California, and so did my family, and so did my wife. And so I said, okay, that sounds great. Let's do that. I was studying the Navier-Stokes equation at the time. I'll apply to those places. I'll apply to a bunch of other ones. And what if I put in an NSF proposal to work with Andrea Bertozzi, which was the author of the first book that I used so much during my PhD thesis, who I'd never met. And my advisor was like, yeah, okay, no, I mean, I know her, so let me do an introduction. And so then I got both an NSF and a UC President's Fellowship to come to UCLA. And that's how I was able to still satisfy what, we heard a lot about what you're supposed to do I mean, you're all here. Many of you are on the precipice of your own, research careers. And it was to, my community at the time, it was actually advice from Richard Tapia and others at the time, and not yet Juan, but later in life Juan, to push the research boundaries of what you can do and become a leader in research. So I went and did that, and then that went great, but I kept having this feeling that I was doing really good research and was doing what people were telling me to do, and I really enjoyed the research, but I had this other desire to also work on these issues around inclusion and community in the mathematical sciences. So I made my first wild left turn, which was I applied to some jobs in my third year of postdoc. I had my first child, and I got a bunch of offers, thankfully, which was great, like 7 R1 offers and 1 non-R1 offer, and I took the 1 non-R1 offer at the University of San Francisco. It was a minority-serving institution at the time in California, and that was a really hard decision to make, but the dean there said, we're probably not going to get you. What do you want to do? And I said, well, it's 2012. I want to launch something called data science. I viewed at the time in 2012 that data science was going to be an opportunity to welcome in a brand new community back into applied mathematics, because I felt the problems were extraordinarily compelling. I was sitting here at UCLA, of all places, and IPAM from 2009, 2012, and there was a shocking number of new talks walking in, thinking about problems like the Netflix problem, computer vision problems. There's some giants here, if you don't know, in this field, and there was real data problems walking into math seminars, applied math seminars here, and I was like, what is this? I'm an applied mathematician. The motivation to get into applied math is coupled oscillators, maybe, if you like that. And if you graduate, it's PDEs and fluids, which is what I did. And that was exciting to me, but that does not attract a large community of people into it. But if I can present problems driven by real-world data problems that mathematicians can grapple and make big advances of, this, I think, has an opportunity to bring in a wider community into this field that I love so much. And really, that's what I ended up spending between that decision till now at the University of Chicago working on. And so I'm going to talk a lot about that, but I'm also going to talk about why the math has been critical this whole time. And this is one of the themes that I've heard throughout this conference that I want to just reflect on and finally show some pictures of people, which is I feel that the reason why I do math is I think of it as a human endeavor. I have written very few single author papers, not because I do not want to, but it is because I do not want to. I actually like to work with people and solve problems together, which makes me a little bit unusual for a generic mathematician, but not so unusual for working on particularly applied math problems. And so I'm going to talk about problems that I worked on with people today. And in particular, though, I show one picture on the upper left because I'm going to encourage people. That was me, I think it was already referenced, was 2012 SACNAS, where I presented my research from the REU, and then flashing forward, this is the REU at MSR UP I was the director of research of, which for me completed like my great ambition of going from an REU student to running as a research director in REU, with the students of the exact same age who then went on to SACNAS and also won a best poster at SACNAS as well. And so for me, that is a math story, but it was also about enormous numbers of people that were involved in order to take that journey. On the bottom left is a typical math photo, except does anyone recognize where that conference is? Yes, I got a couple nods. Casa Matemáticas? They always take the photo in the same place. And so I highly encourage anyone who hasn't been to Casa Matemáticas down in Oaxaca, Mexico, that it's an extraordinary place to do mathematics and that you can organize very much like you can here at IPAM. And then, the right two photos are really the journey that puts me on the boundary of doing traditional mathematics to moving into data science. And in the upper right, it's a little bit hard to see. I'm actually with a colleague, Yannette Intirian, if you know who she is. And that is us holding tickets to a conference called NeurIPS, which for me as a mathematician is a really weird place the very first time I went. In fact, if you told my 2012 self that papers have deadlines and they're 8 pages long, actually then I think it was 6 pages long, and that's a real top flight paper, I would have said, that's crazy, that's not mathematics. But it turns out as you learn about other fields and other disciplines and publishing venues and norms, there's a lot of ways people disseminate knowledge, and that was the first time I realized that a conference proceedings was, depending on where it is, as impressive as getting a A-level journal like an AMS, a bulletin paper, or a JAMS paper. And then on the bottom right, actually, was sort of the last sort of tipping edge of really getting into using data and proving that math works. So we were, when I was at the University of San Francisco, I actually led the sort of pilot data science team at ABC News for the election night. And what they wanted to know was, were they calling elections accurately in real time? And it was 2018, and if you know anything about news venues, they're very conservative. So what you're looking at is actually, it's a little hard to see. In the middle is a famous person, but everyone else around them are faculty, or by and large faculty. And this is the team that tells you, when the bell rings and they're like, we're calling this state or this district for this person or another person, this is the team that does it. And do you know what discipline 90% of them are in? Political science. Yeah, so I need you to know what they did. They cleared where they usually put the cookies that night and put 2 laptops, myself and the head researcher I brought with me. We had a remote engineering team in San Francisco and data science team. And we were a pilot experiment to see if we could call these elections with the data that was streaming in more accurately, quicker, and better than the political scientists did. It was a good night because this is being recorded. I'm not sure I'm supposed to tell you everything that happened that night, but basically what we would do is we would write down, call this then, and we would date and time it. And I don't know if you remember the 2018 election. It was a pretty exciting night, but it didn't feel that way at the beginning, perhaps, depending on how your political leanings are. It felt very uncertain. I'm going to have you relive this just for a second. The polls close on the East Coast, and Florida starts going very conservative, but very narrow voting. And all of a sudden, people are like, oh my gosh, what's going to happen? Now, flash forward to the end of the night, it was a massive blue wave. What was very exciting for us is from the very earliest few minutes of data, we already knew it was a blue wave. So we were pretty relaxed. And by we, I mean only 2 people in the room. The rest of them were actually really nervous. And that was really just the power of using mathematics and data just a little bit more accurately. And for me, I had to put myself through this experiences. I was a tenured faculty member. What am I flying out to New York to do this work for? Well, that's what the rest of them do. But I really wanted to understand, can we put math to the test? And that had convinced me I moved into the right field. In short, though, I really want to say that academically, I've moved around quite a bit. I don't necessarily recommend this to everyone. I think your traditional recommendation is to get very good at just a couple things. Become a world expert in your direction of study for a very long time. That is a traditional route. I'll say I did not do that and had a lot of success, but it was mostly more of my sort of wandering curiosity. So if you're a curious person and need to move around, I could talk to you how to still have a very successful academic career. Well, thematically, there's going to be a lot of, my advisor once said he's made his entire career on, using change of variables because we're analysts. Okay, so, by and large, even though those sound like a lot of different things, made a lot of career on things like, PDE bounds and analysis and dynamical systems throughout everything on that list. But I have been able to move around topically, and really, that's been a really enriching research experience and career for me, and it's the one I continue to pursue, but it is not necessarily for everyone. So, I left the University of San Francisco during COVID to come to the University of Chicago, and I had to laugh a lot when I was hearing what people were saying on both panels, which is I got an email from the University of Chicago that says, hey, you should apply to this leadership position to develop the Data Science Institute at the University of Chicago. So, was already noted by others, I just ignored that and assumed it was spam. And then I got a second email, and I was like, oh, okay. I also ignored it. And then the third time, which was like, look, this is the final time we're going to ask you about this, I forwarded it to a mentor, and mentor was like, you should at least take the call, right? And so fast forward, what I really liked about the ambition and why I decided to pick up and leave the University of San Francisco, a very comfortable place, all my family's in California, to move to a city I've never visited, was it was time that the shared ambition of this field that I've been sort of thinking and studying and developing over the last 10 years was really reflected in this particular vision, which is, our take on this is it is entirely a field building exercise. For most of the last 10 years, data science has looked like, let's cobble some ideas together. I think we've all seen the Venn diagram. You won't see a Venn diagram on my slides because I really don't feel that is an accurate reflection of what data science is. This is cartoonish, but we really view data science, and I've really viewed this for a long time, as a holistic picture in a brand new field. And so it's a different take, but what that means is, yes, of course, there's a lot of mathematics, and we're going to talk about that puzzle piece for the rest of this talk today. Computer science, there's your domain, right? There's your traditional, but I don't think of them as a Venn diagram. They're actually fit together. But what's been missing for a long time is things like communication. And we've heard a lot about that already today and throughout our past. Communicating data, how do we talk about and explain our ideas? The societal impacts of data is part and parcel with how important understanding the mathematical foundations of the algorithms are for this field. Fundamentally, if you're doing a field building exercise, particularly at the University of Chicago, you must identify the missing foundations that no other field is looking at directly, and that's precisely what the faculty at the University of Chicago have come together and done. And for me, what that meant was an opportunity to work on my community issues. So when I was pitched the job, I will tell you right now, there was education and research very formalized under this institute. And I said, let me tell you about this idea called outreach. And this was during the job interview because I don't have to take it. And I'm going to tell you conceptually, very much like in the spirit of this conference and other things we've heard, outreach is going to make our education and research better. That was my pitch. I gave a much deeper and longer explanation of what that meant. But they said, that's a little unusual for the University of Chicago, but that sounds good. And so I said, great, I can keep working here. And so even when you look at our research initiatives, those three pillars are actually now, I haven't figured out a good diagram, but someone's gonna have to help me design it. It's really more of like a triple helix. When we think about our research and the investments we make as faculty at the University of Chicago, we're looking at fundamental problems in the field of data science and also have incredible impacts on society as well as outreach. So our oldest one is something like internet equity and access. The fundamental question we're studying as research is how should society equitably distribute access to data? That's a good question. We do not do it well. That's what we're finding out. We do it extraordinarily poorly, and we do it in ways we have not been able to figure out how to measure how poorly we're doing it. So there was a lot of pieces to this problem to unpack, but each one of these are driven by fundamental problems in data science that have to convene many different faculty from disciplines to come together. The one on the right is a really exciting one for me because I've studied most of my application areas in science, and the fundamental question there is really, I'll paraphrase, scientists will not be replaced by AI, but scientists that use AI will likely replace scientists that do not use AI. And what does that mean on the entire life cycle of doing science, right? And so these are big, ambitious questions, but oops, I just pressed the one button I wasn't supposed to press. What happens if I press it again? It comes back, okay. So in education though, this was a big piece for me. I think if we just design data science major as a traditional method of developing a STEM major, I missed the opportunity to think about representation and outreach. Very few times in our lives at least, do you define new fields that have extraordinary economic opportunities, like things like software engineering. Data science is one of these new opportunities for people. And if we don't think hard about what we do, we may result in a distribution of people that look a lot like software engineers. And if we've heard anything, it's really hard, and you have to put in a lot of intentional effort to push back on that idea. And so when we built things like the major, we thought about a lot of pieces about what brings in students that will select a STEM major that otherwise likely wouldn't. And that went directly into the design of the major at the University of Chicago. Moreover, when we think about graduate students and getting into the field of data science or using data, if you think we're going to change the entire data-driven inquiry research lifecycle at the University of Chicago, that means we have to develop things like a PhD in data science for all, a certificate for all PhD students at the University of Chicago. So if you are a sociology major, you can come and learn data science as a formalized process to enhance your research techniques in your own field. And so we really do want to change it all at once. It takes some time, but it will bring a lot of people that normally do not select a math PhD or normally select a CS PhD or a stats PhD at the University of Chicago into data science. And I think that's a pretty exciting opportunity for me. We think a lot about things like project-based learning, experiential learning, think a lot about the impacts on society when we do this. When I think about the amount of outreach we've done, this slide is a snippet of the groups we're engaged in. And it's also to show the ambition and investment into that third pillar, right? So on the upper right is actually the community itself. There's data science problems in every one of those organizations, from the UNHCR all the way down to 100 Black Men of Chicago. And we're engaged right there at the front in research problems, engaged with our students and our faculty. When we think about our academic partners, the University of Chicago could just lean over to our other friends that are in our peer group and say, hey, why don't we do some data science together? But intentionally instead, we built a network of HBCU and HSI and minority-serving institutions to learn how to scale out the data science we can learn together so that many institutions can engage in what we've learned in. Often it is the case that a very large, well-resourced university like the University of Chicago can do something, and then we think, hey, we did it, here's how to do it, and we tell the world about it, and we're always a little bit concerned why no one just did exactly what we did. But it is largely by who develops these education programs, who develops these research programs, and so we think the most scalable and highest impact opportunities actually partner with universities that are, represent much more of the population than the University of Chicago. I'm going to end here because we're going to get into the math next, is really to the ambition of how much we want to get outside the university's walls to make impact. So we are now working with the city colleges of Chicago to develop data science with them and at the University of Chicago at the same time. But if you have worked in or are working with currently community colleges, there's a lot of challenges largely around resources and the challenge of the student population. So they came and asked us if we had any opportunities to partner in data science. We said 100%. Formalizing a joint faculty committee between the University of Chicago faculty and the city colleges faculty around the development of data science at the city colleges, but also a recognition that they are not going to recruit data science faculty there on their own. So to meet that need, we actually developed a teaching postdoc called the new Data Science Preceptorship, where they get mentors from the University of Chicago and the city colleges to develop their teaching portfolios at both institutions. We feel if we're to develop the education leaders in data science for the next generation, experiences learning how to teach students at the University of Chicago and the city colleges in a combined effort is going to make them much better educated than the ones that just learn how to teach UChicago students. And so I'm excited about this. This is the work we've been doing only in the last, what I've presented so far in the last about 12 months. So I will give you an update next year to see what we're up to. These are a lot of the external groups we work with when we think about social impact. And again, it's pretty exciting work, but it's time to talk about the math of data science, because that's why we're all here, or at least why you have to listen to me for a little bit longer. And the best part about putting this talk together is how many times I had to change the talk after watching people give talks all through the week. So I had about 15 slides on this, but then I just decided, I hope you saw yesterday's talk, because I had all these animations, I was working hard to do. I was like, oh, forget it. This is such a beautiful talk. It really explained the core ideas. But I feel like, we have a lot of the mathematical community here. And I think areas like algebraic geometry, we heard about, areas like topology, areas like I'm going to talk about next after this, are beautiful areas that have just as important impacts for data science as what you normally would think of maybe in the computing areas. And so I'll just add that the ideas that are there were ideas we explored at the MSRI UP, program, and here are the three students and postdoc Paul. Now he's faculty at the University of Philippines, Ignacio. And there, again, we worked on problems that really drew students in. We were trying to classify atrial fibrillation using topological data analysis. As you heard yesterday, it works, and it works extremely well. And there's competitions in which you can try out your algorithms to find out if they work really well against state-of-the-art deep learning algorithms. And in many cases, topological data analysis are working just as well as a lot of those techniques you're much more popularly hearing about. But one of the big challenges that wasn't quite addressed yesterday that has been of interest to mine is one of the reasons why, and again, maybe I'm already a little out of date, topological data analysis hasn't taken over the entire world, is it's very expensive to compute. And we think of deep learning as being very expensive to compute, but there are things in topological data analysis that are very expensive, and people are working really hard to speed them up. We were working, for example, we learned about persistence diagrams. Persistent diagrams are the things that you can translate these data sets into, beautiful topological objects that represent those data sets. Well, one of the things you want to do in classification is to understand the closeness of topological data sets, and for that you need things like the bottleneck distance. And those are very expensive things to compute. And so we worked recently on developing an extraordinarily fast speed up to the bottleneck distance. And those types of things take a lot of mathematics, right? And without them, and as we heard yesterday from Jose, without those foundations, we are burning CPU speed and GPU for almost no reason, right? So mathematicians are making huge advances where people are just turning up more compute, and I think we can be more thoughtful. And so that would save me just to one slide on TDA, which saves me to talk about algebra. We haven't heard enough about algebra and data. Now, when I say algebra and data, the first thing I think you're probably thinking of is not another comment on SVD or PCA. I understand it's really important. It is really useful. We're gonna use it a lot. And so this talk, which I'm gonna kind of speed through because I want to be mindful, we're doing okay, is not about that kind of algebra. This is for any group theorists in the room? All right. That means I can go quickly. So just to show that when I mean math has a critical role in data science, topology you might have been like, but then of course Jose came and killed it yesterday, so you're like, I'm convinced. So again, what about group theory? What about algebra? And I'll argue there's almost no part of the mathematics spectrum that you guys are learning. We even saw a little debate between algebraic geometry's uses right here during the panel for data and applications. Again, here's another group at MSRI UP. So I threw one group a topological data analysis problem, I threw another one a non-abelian Fourier analysis problem. And what was shocking about this experience was it's only 6 weeks, and we used 2 of them to train up the students in these fields, and they have 4 weeks to actually do the research. And all the groups either published something at a NeurIPS workshop or in a conference proceeding afterwards, or it's still under review, it's been a while. So here's the group that was largely responsible for the work I'm about to talk about. And I believe, I should say this, Rosa Garza is a graduate student here at UCLA. So they are all doing quite well. The problem we were going to look at is a genetics problem. We saw genetics today, so again, I'm going to reference another talk and shorten what I'm going to motivate for. But the problem in particular we're looking at in a genetics problem is this idea of epistasis. Has anyone heard of epistasis? Okay, yeah, of course, the ones that know. So I'm being very, very terse in my description of these things. It's one of the reasons why, though, that we have not solved the human genome problem, right? Is that we cannot predict, now that we've sequenced the human genome, everything that's wrong with it. Now, it's not really true. It's one of the reasons why. And fundamentally, the idea is you can do a lot with these enormous gene expressions like GWAS and QTL, but it's really hard to understand interactions between genes. It's just really hard. It's a hard computational problem. It's a hard math problem. It's actually a hard science problem. We can also talk about environmental interactions and many other interactions, but I'm going to focus right now on the idea that perhaps single genes don't individually contribute to particular phenotypic expressions, but it might be higher order interactions, but they're so hard to try to measure that we kind of just don't bother. And that's really what this says. It's a severe challenge. When N is enormous, and we're talking millions, then n choose anything is way worse than n, right? And so when we think about interactions, we're looking at n choose k, and that's a really bad problem. Okay, so I'll tell you right now, we did not solve that problem, but I'm going to tell you a little bit about what progress we made. Just briefly on the types of epistasis, we're just thinking, this is a cartoon. You know, you have two things, you have two, let's say SNPs in this case, and you know, if they're capital, they're mutated, and if they're lower, they're not. And you know, in the upper left, it basically says if X is mutated, it moves up the phenotypic response. If they're both mutated, it jumps again, so it's very sort of additive in its behavior. But you don't actually see that even among a pair. You can get complicated relationships even among pairwise phenotypic responses, which makes things very challenging. I will just go ahead and say Alejandro did a much better job of this picture, and so I will leave this at, we're going to look at some these single nucleotide polymorphisms, which are SNPs. And again, at this point, you might say, what does this have to do with algebra? And so let me just remind, I learned Fourier analysis, and I learned it at Harvey Mudd, and I learned it in a weird way. There's a Fourier transform class, there's a Fourier analysis class, which I eventually did take. But I took 4 semesters of algebra. So I thought Fourier transforms were like an algebraic problem. And I'll explain how I learned them and actually how it informed what I ended up using, which is, if we remember, traditional Fourier analysis, which is what I'm going to talk about briefly, is you have a signal, and the idea is what happens if I think about expressing this signal as a sum of frequencies, and can I learn something from this signal that otherwise I wouldn't get from that sort of messy looking thing. And so on the left, you have a time domain. You press the theoretic Fourier transform button, and you transform yourself into a Fourier domain. And what you see is large spikes in specific intervals. And then we quote and say, well, those are the seasonal dominant expressions of this time series. And then you feel quite good about that in terms of understanding. As just a quick reminder, there's formulas underneath this as well. So you really say, I'm going to represent this original signal as the sum of inner products against a basis, plus the basis times the basis, and you can reconstruct that signal from the Fourier spectrum, okay? And so that is your traditional Fourier analysis. You know, I think I say this again as a summary. Again, F is the sum. It's a function on a set. That's important, group theorists. And then expanding F in a new basis gives insight on that behavioral function. So that's what, you know, the Fourier transform has not fallen out of vogue. It's still used constantly. You don't hear as much about it in things like deep learning and data science, but you should hear more about it. But where does the algebra piece come in, right? And it's simply because that set of basis functions that we use that have periodicity it turns out you can think about them in an algebraic framework as an abelian group, and they're a cyclic group. And so we're projecting these signals, particularly in discrete Fourier transform, onto a cyclic group. And you get something out of that. You like learn an interpretation. If you see a high coefficient in front of 2, we'll say there's a period 2 behavior in this particular signal. And that's really useful. But that right now does not have anything to do with genetics, but that's the hint, okay? So the data we used is this public data set. This is a trial. You know, when we think about data and data issues, and you think about genetics issues, things we did not want to use right off the bat were any human data, no matter how necessarily anonymized it was. And so we've specifically used mice, and mice just because they have less concerns over their privacy than humans. And otherwise, they also have really great phenotypic measurements. So things like body mass is a function of genetic expression, bone mass. You can actually get really into the weeds of understanding what are these reactions to gene expression. And so when you look at the original paper, this is how they publish the results. They like write down all these chromosomes, I cut them off eventually, and then they do these computational studies, and then they draw these like little lines on these chromosomes, and they say, hey, look, body weight. We see some reaction to body weight there. There's lean mass and fat mass and muscle mass and other things. And they're really sort of identifying in these computational studies these individual areas of the chromosome, these SNPs, or a collection of SNPs sometimes, that have a phenotypic response when they're mutated. So what we did with data like that was that we then just for sort of a trial and error basis, we looked at 16 of these SNPs. You can scale this up quite large, not to millions, but for the sake of the study, we looked at these 16 commonly looked at SNP mutations that have been overstudied in this space. And it's even in that space, it was really hard to find positive signal, statistically meaningful signal in that. We thought, great, let's apply a Fourier transform to this data and see if we can see something better, particularly when we're trying to think about the problem of epistasis. Look, there's one of my first typos. And so when you think about the group structure, so our data set now is, let's say, 16 chromosomes. We learned last time that you can actually have like 0, 1, or 2. So just bear with me right now. Let's just call it 0, 1. We can do 0, 1, and 2 with a Fourier transform as well, but we only had 4 weeks. And the group structure is easier if you just do 0 and 1 right now. So again, if you have a 0, 1 response, your data looks like a column of 16 plus the response, say, mass or whatever on the 17th, and then a whole bunch of mice. Okay, so it's a tall, thin matrix, and it's a bunch of zeros and ones and then a final number. Okay, that's your data set. And when you think about the Fourier transform you want to apply to understand whether mutations are interacting with each other against a phenotypic response, it'll turn out, if you think about it, that the symmetric group is the right group to think about there. And that was well understood and first kind of pointed out by Percy Diaconis. And so what we do is we just take that data set and apply a Fourier transform against the symmetric group and look at the spectrum of that. And the spikes in that spectrum will represent in higher order interactions as a reconstruction of the phenotypic response. So, for candidacy again, so we take, this is what our Fourier transform now looks like. It's a bunch of irreducibles. The big difference is when you have a non-abelian Fourier transform as opposed to an abelian Fourier transform, you don't get these single basis elements, which makes things a lot more challenging to interpret, but you can interpret them anyway. And then this is really a cartoon of what this looks like, is you have this original data set, and then you break it down into all its higher order interactions, and you look for tall spikes. And it's expensive, but what was really nice is it works. So the original study had no ability to find higher order interactions in them. We basically just press the Fourier transform button, and we start to see things like this, right? So if you start looking at the high spikes in the Fourier transform, what you see is, so what we did in the encoding is instead of writing out those SNPs in those complicated RS long numbers, we just gave them A through O. And so what we were looking for is interactions of A through O. And what we first saw is one of the largest spikes we had was something called ABM, which had not been observed together as a high response. I believe this one was on, I think it was body mass, but yep, there it is, body weight at day 70. And it was a massively large detection of interaction, and it came through just purely the Fourier transform spike. Here's another one, a fourth order. When I say fourth order, that's n choose 4. If you're doing n at a very large number, we usually do, like, some of the good stuff is now n choose 2 right now, which is capable. And with this sort of machinery borrowed from representation theory, we could start looking at higher order interactions as the same kind of structure as we would any other order interactions. And what you can end up doing here is, again, we saw much stronger p-values before, as you should in a true genetic study. But we're looking only at, we've already reduced ourselves to 16 identified potential interactive sites. And so you can actually discover brand new higher order interactions, which for us is pretty exciting because it was a proof of concept. With something like this, you would go and work with a geneticist and say, like, let's conduct a study. If we can really start leveraging Fourier transforms to hint at higher order interactions, we might have something together to work on. And so that for the students was extraordinarily exciting, and it was certainly extraordinarily exciting to me because I did not think it was going to work. I should have said that. But when you give a REU project out, you like have some ones that you're like, this is definitely going to work, and others are like, oh my God, I hope they learn something. And that was on that side. And I knew they'd learn something because non-abelian Fourier transform is a lot to swallow in a 2-week training. But we actually got some really exciting results from it. And so, what I think of is there's so many directions like this that mathematicians can just drive a truck through. If you think about what a non-abelian Fourier transform is, you can view it as a convolution, right? And so if you think about it as a convolution, what is the hotness in machine learning right now? Not anymore, but still used. Things like CNNs, convolutional neural nets. And convolutions are very well used in the machine learning information. Everyone, especially if you attend a conference like NeurIPS, is looking for the edge on the new mathematical idea that proves value. So what happens when one starts thinking about machine learning algorithms based on underlying group structures of data? There's a few people that are working on that, not a lot, because you have to bring and bridge a lot of communities there to get there. But again, this is just the tip of the iceberg of things I think are pretty exciting that mathematicians can really take a leadership role in understanding. So again, we always thank our sponsors before the talk's over, and those were some of them there. I think we're in pretty good shape. I'm actually gonna probably skip this one because I think I have about 9 minutes. But I started moving. One of the things that is in that study in Bakersfield as to why it's such a bad place to grow up is like it has some of the highest asthma rates, particularly juvenile asthma rates, which particularly affect our community. And I had this opportunity to start collaborating with this institution called the Telethon Kids Institute, which happens to be in Australia, that looks at pediatric asthma. And they had some seriously hard problems that they wanted to look at that I thought at the time we could make a lot of progress using the machinery of data science that we had. And what it boiled down to in a lot of applications of data science at the intersection of medicine is something is painstakingly hard to do currently, and if there's an opportunity to automate that or assist that in a very advanced way, then it's kind of worth trying out. Because any incremental effort you make there saves a lot of money, medicine's very expensive, and also impacts a lot more people. And so the core problem is the diagnosis of asthma and cystic fibrosis is actually a very difficult long-term thing. And one of the techniques that's used, particularly in Australia, is you basically, like if you're coughing a lot, you spit onto a slide, they slap it down, they stain it, and then they look at it under a microscope. That's the thing A, and then on the right, there's a diagnosis. And I want you to know the way that's done is a human stands over the microscope and counts something like 500 cells that they can find, and they're supposed to pick them at random, so you know how good humans are at that. And at that point, there's like these weird conditions that says, yep, you have cystic fibrosis, or yep, you have asthma. And it's a ratio of a lot of different types of cells that they're supposed to count really accurately. And so that is always an opportunity. But in order to get these same lab technicians on board for this, I said, well, we need you to label data. We need you to label images. And if you give them 4 techniques from left to right, you can imagine they loved the left one the most. So on the right, we asked them to color in and fully segment a cell and then classify it. There's these 4 different cells. And then the next one is like, how about bounding boxes or extreme points? And finally, can you just put a dot in the middle? And it turns out if you really want to do research in partnership with people outside your community where you ask them to do a lot of work, you got to make things as easy as possible. So it turned out they were going to quit the study unless we did this, just put a dot in the middle, because it was a lot of work to ask them to do. And so what we had to decide now is how do we develop algorithms, how do we use mathematics that would normally benefit from full segmentation, but it takes 708 seconds per cell versus per whole cell versus 70 for center points. What can we do with that? So if you do this, we had 4 trained annotators. We asked them to do this across a lot of different patient diagrams. You could see the 4 cells on the right there have very different distributions and shapes and sizes, and they're very actually hard, as it turns out, really hard to get agreement among all of our own annotators. This is a common theme in problems like this is, for things like making sure it is an immune cell, there's pretty good agreement, but things like lymphocytes, people are all over the place in agreement. And those are critical aspects of diagnosis. And if you think about the ICC, even in the, I'm just gonna say the third one, those should give you pause as we're making medical diagnoses on that level of variation. And so, what this meant was the human aspect of this is already really hard. And so, we developed a computer vision algorithm, I'll just leave it on the screen for just a second, to do a lot of that work and to see how well we could do. And the long story short is we can match the assessor's capability, which means we can process a lot of images at like light speed with very similar levels. And this is all out-of-sample stuff. So this is on full out-of-sample test stuff. And so for us, what this means is we can start thinking about the way we could develop software and tools that aid these technicians in the work they do to handle much more volume than they normally can get to. And so that, for me, was something I'm pretty excited about. In data science, you always have to think about benchmarks or your referees kill you. So you have to go back and show that this works on benchmarks. So let me just, here's the final thoughts, and these are going to be a little out of order, which is basically, I hope I've shown you that math has an important role. I've never left the math community, even as I'm technically my academic appointment's in the computer science department at the University of Chicago. Data science I view as fundamentally led and principally driven by mathematics, and it's really to deal with issues like this. There's a lot of black boxing that's going on right now. This is kind of the funny version of that black box, but now think about those societal impact issues. If we really do not understand what we're doing, then we really are at sort of an existential issue of like, should we be doing this if we don't know what we're doing? Particularly when there's harms being done right now with the use of these algorithms, right? And so, we started writing papers on this area because it bothers me that much. And if you think about AI or machine learning, at its core issue, it is to optimize a metric. And it is at its core issue to turn a metric into a target. Well, any social scientist or any scientist might know how bad a problem it is when you turn a metric, aka something you're measuring how well you're doing, into the target of the algorithm. It ceases to be a metric. And there's all the intended consequences and unintended consequences of that. But at the core, a lot of non-thoughtful AI is doing exactly that. So a lot of the issues that we find that are coming out of the impacts of this work are fully explainable before AI actually existed. And so when I think about this issue, the people that are harmed by this are usually people with the least amount of power, okay? Because it's a human endeavor. Math is a human endeavor, data science is a human endeavor, and it has traditionally been people of power that are developing these algorithms and using them. And so I challenge this community to get deeply involved in data science through mathematics, because I think we can, sort of be a powerful voice in these issues. And so this is my first plug. I've already heard what should we do next, so I'm gonna just plug something that I loved. I went to the Modern Math workshops as I think the very first one, and I'm honored, but honestly don't come to mine. Moon Duchin is amazing, and I think both of these particular, so Mario and I, if you recognize that face, he was a postdoc when I was at MSR UP, he's now faculty at Fresno State, and we're co-teaching the data science, mathematical data science, a mini course, but Moon Duchin's Modeling Democracy is gonna be just as exciting. I'm gonna try to sneak out to watch it. But if you're wondering where to go next from something like LatMath, this is a good start. And then, yeah, so I'll just leave that there. We're hiring. Okay.